Hello, welcome everyone. Feel free to say hi. I've got the chat open, so it'd be great to hear from people. Hope we're all doing well and everyone's keeping well. We've got a nice GCSE topic to look at today, functions. It's quite a big one. Welcome. If you're here, feel free to say hello in the chat and it'd be great to hear from everyone. And we'll get started shortly. So let's have a little look. Excellent. Right. Cool. So I'm going to share the screen and we'll get started. But if you're just joining, do feel free to share answers and ask questions as we go in the chat. And I'll do my best to answer them as we go forward. Functions, this is a really good topic to be looking at for GCSE, for GCSE maths. It's one of the ones that a lot of schools and colleges and anyone teaching functions leaves this till quite late on because it brings a lot of things together. So we're looking at a really important topic for the GCSE here. I'm going to share the screen and then we'll get started, but it'd be great to hear from you all in the chat. And as I said, feel free to say hi and share questions and answers as we go. Cool. Right, here we go. We're going to have a little look at the following. So hopefully everyone can see that. Make it nice and full screen. That's excellent. Cool. Welcome if you're just joining. We're looking at functions today, advanced functions. So this is kind of the more involved bit of the GCSE that really carries on through to A-level and beyond. So functions and the notation is all really important. It'd be great to hear from you as we go through these, but I'm going to whiz through this topic and we'll look at some exam questions and stuff as we go. So welcome. Hope everyone's having a nice weekend. And yeah, well into the new year now. So yeah, big topic and we're going to get started. So to start with, I'm Max, I'm head of maths at SnapRevise. I did a maths degree and I've been teaching maths ever since. So that's a quick little bit about me. And we've obviously got these sessions running each Sunday. So hopefully you've been along before, but if not, this will hopefully be useful for learning about functions and perhaps for some of you it's revision as well. Right, here we go. So what we're going to look at today is we're going to look at writing functions using the f of x notation, look at how to find an inverse function, and also find the composite of two functions. So we're not going to do graph transformations and we're not going to do iterative methods because this topic sort of straddles lots of different things, but these are really main ideas that we're going to look at today and they are quite involved. Let me know if you've done them before as well. It'd be great to hear answers and stuff as we go. Welcome to anyone joining. Please do feel free to say hi. It's great to have you in the session here, able to work through this stuff. As I said, very important at GCSE and beyond. Hi, Mariam. Welcome. And Annika, welcome anyone who's joining, saying hello. And it's lovely to see you guys engaging in the chat. So hopefully going forward, this would be great. Welcome. Excellent. Welcome, Mohammed. And anyone else joining? I'm just trying to keep check of the chat as we go. Right, I'm going to get started. So let's begin. So this topic, as I've said, is really important on all the exam boards. It's very much an important higher tier GCSE maths topic. So functions is something we want to be really familiar with. We've done a lot of the surrounding ideas all the way through school. Starting with this sort of basic principle, maybe of a function machine, you might have seen much lower down the school. So we take an input, we put it into the function, and then it spits out an output. So what would happen here? So we can kind of do the in-between step. So if we take, for example, 8, this function multiplies it by 3, and then what it does is takes away 4, and the output would be 20. Now, in terms of any general input, if we call it x, could anyone tell me what the output would be if we used x? So we've taken 8 as an example. What would be the output if I put the input in as x? So we're going to think about the two steps that go on and what does it ultimately spit out. So x goes in, gets trebled. Please share in the chat if you think you know what the output is already. This should just be a bit of hopefully a nice introduction into what we're doing. Brilliant. Yeah, superb. So 3x will be the sort of in-between step and ultimately the output will be 3x minus 4. Whatever goes in, it trebles it and takes away 4. Brilliant. Well done, guys. So the next one, 13, we're going to add 2, and then we're going to divide by 5, and the output will be 3. Now, algebraically, this one is a little bit more involved. If we take x, let's think about the process. We're going to add 2, and then all of that gets divided by 5. So I'm going to write it like that, and that would be the output for this one. So that's sort of a real basic recap of function machines. Moving forward, though, we're going to look at the more advanced kind of function stuff today, as I mentioned. So inverse functions. Who has seen this before? Let me know if this is something you've covered before, inverse functions. The notation is really important here, and also like the principle of why we're doing this is quite important. So inverse functions, the notation f of x means, if we really sort of define this, that the function that we're calling f, the function, and the function is almost named f. Okay, cool. Yeah, so it's maybe an idea we're sort of familiar with, but maybe we haven't gone fully in depth with how to find the inverse in general before. Welcome if you've just joined. It's great to see lots of people joining, and it'd be brilliant to hear from you all. So the function f applied to the input x. That's how we would sort of read that. And sort of in simple terms, f of x is what we often read it as. So we're taking x as the input and subbing it into the function that we're calling f. Right. So what we're going to do is we're going to take, for example, this function here. If I put the input in as 2, I'm just looking at the chat. Was that a question about downloading the slides? Yeah, hopefully that will be doable. There might be a link available that you can download soon. Hopefully we'll get that sorted in the chat. But I'm going to carry on with this for now, and feel free to share answers and questions as we go. So 2, I'm going to add 5 to it, and then I'm going to times that by 3, and that would spit out 21. So what we've basically done is the general function here, f of x, is equal to x plus 5, and then that all gets times by 3, all multiplied by 3. So that is the function. So what we've done with 2 is I've put 2 in, added it to 5, and times all of that by 3, and the output is 21. Brilliant. Okay, yeah, so hopefully you guys can see the link there for the slides. That would be great if you'd like to download and work alongside this, or keep this for revision. Right, let's look at this one here. So we've got an input x, and what happens in this function is we take away 4, and then after that process, we square root the whole thing, and the output will be the root of x minus 4. So if we put 13 as x, we take away 4, we get 9, and reroute it, we would get 3. And I'm taking the positive square root here. Brilliant. Right, so hopefully everyone's happy with that. Now, just looking at inverse functions as a sort of basic scenario, and then we're going to go a little bit more in depth with the notation. So the inverse function, we denote using this here, and we need to be really careful with the notation. So f minus 1x, f, that's the inverse function of f, of the function f. You might have seen a very similar thing before when you've done trigonometry and you use the function sine or cosine or tan. And then on your calculator, you click shift and it comes up with this sort of notation. That's function, arc sine or inverse sine, is the function that undoes the sine function. And it is very sort of consistent notation with this. Right. So let me just have a little look. So if you want anything recap, did you want me to re-explain anything there? Hopefully that's all clear. But if you want to sort of look over this, feel free. I'm going to move on now to this inverse function here. So the inverse function is basically the function, if we're defining it, that undoes the original function or reverses it. So the function which does the reverse of f. So hopefully that principle we're quite familiar with, and it sort of makes sense. Does the reverse of f. So it will take an input of f of x and give an output of x. So it basically reverses the process, it undoes the process. So for example, this function here, which doubles it and adds 7, we take an input, which I'm calling x, times it by 2, that gets me 2x. And then from there, I add 7 as the next step, and that produces 2x plus 7. So whatever I had, I now have double it plus 7. Now this function will take the first thing and rewind this process and do the inverse operations. So I'd have x minus 7. We've got to think what order it would do it in order to undo the steps. So we'd have x minus 7 over 2 would be the inverse process. And the order is very important. We're going to look at this carefully shortly. So for f of 2, if I put 2 into the original function as my input, what would I get as the output? So 2 subbed into this function here, which doubles it and adds 7. What is this going to spit out? What is this going to produce as the output? So f of 2 would produce what? So if I take 2 as the input and I sub it into the function, and welcome to anyone who's joined. It'd be great to hear any questions and answers as we go. Right, so let's have a little look. Brilliant. So if I put 2 in, I'm going to go 2, lots of 2, plus 7. So what's that? We'll check 4 plus 7 is 11. Well done, guys. That's lovely. So that would be the output. Very well done of subbing 2 in. Now, just to check that, if I put 11 into the inverse, which takes away 7 and then halves it, it reverse engineers the process and I get 2 coming out. Lovely to hear from you guys. Thank you so much for sharing answers. That's brilliant. And hopefully what we can see has just happened is if I substitute 2 into the function, I get 11 out. If I take 11 and put that in the inverse function, I get 2 back out. So it sort of rewinds the process and takes the output of the original function and gives me the input of what I must have put in. So it's a really important idea or concept to understand that that's what the inverse functions are doing. So we're going to keep going. We'll do a couple more examples that get slightly more involved, and then we'll see how this would come up maybe in light of an exam sort of scenario. So very well done. I'm going to move this on. A couple more examples for you guys to think about, and please do continue to share answers, but also ask any questions if you're unsure. Here we go. So this time, this function takes away 3, minus this 3, first of all. The first thing that will happen, the order is very important. And then what it does is it divides it by 4. Now, if you guys want to work out what would happen then, if I substituted 15 in as the input, and while you're doing that, I'm going to write the reverse process on here of what the inverse function will be doing. What would be the undoing process? Okay, so if I substitute 15 in, very well done if you've done that, and you're probably anticipating how these questions are being designed already, but well done. You'd get 15 minus 3 divided by 4, which ends up as 12 over 4. Very well done. That produces 3 as the output for 15. Superb. Thanks very much, guys. That's lovely, and hopefully we all agree we're all happy with that. Superb, and great work in shown as well, which is really important. Right, so if I now put 3 into the inverse, and this is a good thing that allows us to check our answers as well. If we put 3 into the inverse function, which does 4x plus 3, 4 times 3 is the input plus 3. It's going to be 12 plus 3, which produces 15, as we would hope for, as we would expect. Very well done. That's great. Now, this one here, if this is the original function, first of all, could anyone tell me, and you might have to go in 2 steps, what the inverse function of this would be? So let's sort of think what goes on here, and the sort of order of operations or BIDMAS or BODMAS or however you've learned it is really important. We're going to square it first in this function, and then we're going to times by 6. And so many people get this wrong because they think, oh, 6x, and then I square it all. But you don't square it all. You're squaring x, and then you're timesing x squared by 6. So what would be the reverse of this? What would be the inverse function? Let me know if you've got any ideas. It might be a bit of a challenging one to type in, but we can kind of be creative with how we write this in the chat. But if you can explain what you think the inverse would be, and then we can try it with the numbers, absolutely. So kind of reverse engineering this process. The last thing we did was times by 6. So we're actually going to divide by 6. Excellent. That's superb. And then we're going to have to square root. So then where we squared it, the inverse would be to square root it. So it would be root of x over 6. Well done. Brilliant. Superb suggestions, guys. That's lovely. So if we put 2 in, I think some of you have given a go to this one already. You put 2 in to the original function. Let's be really careful because it's a classic mistake at GCSE, the squaring and not doing the order of operations and just kind of rushing through. We're going to square it first, then times it by 6. So using order of operations, you do indices first. So this would become 6 times 4. So your output would be 24. Very well done if you got that. And hopefully everyone agrees and can see why we have to do it in that order. Now, undoing that, let's check it. You're going to square root 24 over 6. So that is effectively the square root of 4, which we hopefully know to be 2. And we can see again that it's reversed the process. Right, that's brilliant. So we'll do a couple more of this style, because this is very much of the sort of flavour that you'd expect in the exams. And then we'll do a little checkpoint and some exam questions and move on to composite stuff. Yes, very good. Superb. As I said, guys, please do let me know if you've got any questions, but also if you want to continue to share answers, that's superb as well. Who has done this before? I mean, hopefully these ideas are relatively good to follow, but it might be a topic that's very much revision for some people, and for others it might be quite new, particularly the notation. So let me know, and we're going to crack on with these next couple of questions. So here we go. But yeah, it'd be great to hear from you. As it's this sort of time of year, I think GCSE students start covering functions in a lot more depth, and it is a topic that really grows. Right, lovely. So this function here, what's the f function in this question doing? It's taking an input x, and the first thing we're actually going to do is subtract 9. And then with that, what we're going to do is we're going to square root it and get root x minus 9. Oh, okay, no worries. So very well done, especially if you've had to sort of guide yourself through this topic. But it is an important one. And as I've mentioned before, functions is something that carries on into A-level and beyond. Right, let's go through this. And then hopefully if it's feeling a bit samey, we're fairly confident with these ideas now. So let's have a little look. Reversing it, we're going to square it. Oh. Squared, and then we're going to add 9. And they're both sort of the inverse of each other. That's another sort of fairly important comment to make. So here, 25 minus 9, so it's going to be root 16, which is 4. And then the inverse of 4, 4 squared, add 9. So that works. Very good. Right, now the next one, this is actually all factorized up. Now, some people think we need to... let's have a little... Oh, brilliant question. That's a really good question to ask, and something that's worth us really clarifying because it ties in with surds. You can't separate 25 and 9. Because it feels like maybe we should. And I think because we're dealing with like a Pythagorean triple, interestingly there, it looks like that's a thing. You can only split surds up when it's multiplication and division. You can't in general say that this squared minus this squared and take it out the square root and take away and add and subtract. That isn't a thing. That's something we need to actually be very cautious with. So thank you for raising that question. We shouldn't really break that up in general. It just so happens for this example, it does work because they're nice Pythagorean numbers. But for most things, we've got to be really careful with that. So that was a lovely question, and hopefully everyone's kind of picked up on that as well, that we do need to be careful here still with that. Well done. Right, I'm going to quickly go through this one, but if you're ahead of me, where did the 4? Oh, so good question. So for the inverse function, I've put 4 in as the input here, squared it, and then added 9. Yeah. So I'm putting 4 into the inverse function this time, squaring it, adding 9, and getting 25, which I was actually hoping for, because that was the input of the original. Okay, so hopefully that's clarified it, but very good questions coming in. Okay, right. So these next ones, if you guys want to work ahead of me, feel free. And actually, the fact that this is factorized is really handy, because the first thing we're going to do is, going backwards, we would divide by 2 first. And then we would add 6. Lovely, good. That's great. Thanks for the questions though, guys, because it's really useful for clarifying the finer points. So that's really good. Right, let's sub 10 in to the original function. 10 is going in here. So it's going in here as well. And let's see what we would get. Great. So if we put 8 into the inverse, hopefully we're happy that that should spit out 10, because it should undo it. So if I put 8 into here, 8 over 2 plus 6 is 4 plus 6, which is 10, as we would expect. Cool. Right. So I'm going to keep going, but very well done with that. Little checkpoint, if you guys could let me know in the chat, just a honest bit of feedback on how you feel with that first bit about inverse functions. So how do we feel with that? And then we'll look at a couple of actual exam style questions before moving on. And then we'll be looking at composite functions. So the notation is quite important. If you could just give me a 1, 2, or a 3 in the chat, that'd be lovely. Just give me kind of an honest idea of how you feel with that bit of functions. Cool. Lovely. Right. And what I'll do, just move this on so we're ready to go. But yeah, as I said in the chat, let me know how you're feeling. That's lovely. Here we go. So this question, you are given that f of x equals 5x minus 7. Calculate f of 5.2. Okay, so what we're going to do here, and feel free to work ahead of me. So if you'd like to just have a quick look at this one here, is this the one we wanted to check? So we subbed 10 in and we got 8, and then we subbed 8 into the inverse, divided it by 2 and added 6. And that gave us 10 as the output of the inverse function. Okay, I'll go back at the end if there's anything that still needs clarified, but hopefully that's okay. Right, anyway, let's have a little look at this one. And as I said, do keep me informed if you need me to clarify anything. But if you guys want to work ahead of me here and put 5.2 into the function as x and see what it spits out, that would be superb. Brilliant. So if I sub 5.2 in as the input, so I'm doing f of 5.2, which would be 5 lots of 5.2 minus 7. Let me know what we get out. So what output does it return? What does it spit out after the input of 5.2 has gone into that function? So that function times it by 5 and then subtract 7. What do we get out? Let me know. Lovely, well done, guys. So that returns 19. So this one looks quite interesting. Work out for an expression f of 2 plus 3t. Write your answer in the form at plus b. Now, even just the style of this question throws people off. Well done, guys. Thank you so much for the answers. That's brilliant. This one I want to go through carefully because it's still the same function f, which times it by 5 and minuses 7. But this sort of thing really throws people off. So the input now is 2 plus 3t, whatever that is, that's going into the function as x. So what I'm going to get is I'm subbing 2 plus 3t in wherever there's an x. So I'm going to get 5 lots of that thing, 2 plus 3t, and then I'm going to subtract 7. And all I can do with that is tidy it up algebraically. So if I expand that single bracket, I'm going to get 10 plus 15t minus 7, collect the like terms, and we're going to end up with 15t plus 3. And that actually is the answer, because that is in the form something t plus something. Okay, so this question suddenly looks a lot harder, but actually all we're doing is we're subbing this algebraic thing in as the input, timesing it by 5 and taking away 7 and tidying it up as far as possible. So the answer is in terms of t. But that's all we can kind of really do with that. We've still applied that function to it. We've put that in as the input, seen what it spits out as the output. Okay, so hopefully that's kind of clear. Please do ask me if you need anything clarified though for that. And let's keep going. So let's have a little look. Right, so another exam style question. Here is a function, input, add 14, times it by 5, and then you get your output. So the output of the function is x. Write an algebraic expression in terms of x for the input. So this is kind of like what we were doing. X comes out, so going backwards, what would we have had to have done? The first thing we would need to do to reverse this process is divide by 5, which algebraically is like x over 5. The next thing we would have to do is subtract 14. And so this is what we get. And that is your answer. Okay, cool. Right, so we've got a couple more questions. Oh, we've got another question, and then we're going to look at composite functions. So if I move this on slightly, hopefully that's good for everyone. Let's move this on. Here we go. Right, can everyone see that? Now it says a number k is put into the function a, and the output is also k. Find the value of k. Right, so I'm going to try and define this function using the sort of function notation. Now I know that what this is saying, that if I put k in, it actually spits k out. Okay, now this function, if it was in terms of x, would be x plus 14. So this would be 5 lots of x plus 14. Now, what we're actually doing is we're putting k in as the x. So we're going to get that 5 times k plus 14 will come out as k. So this is what's happened. I've put k, whatever they've just chosen to use the letter k, in as the input. I've added 14 and times all of it by 5, and the same number has come out, which seems really bizarre. Like, how can that happen? That's what we're going to solve. So we now have an algebraic equation to solve. So give it a go. It does seem a little bit strange that this could happen. Have a little think. How would we go about this one here? So if I expand this bracket, okay, let me reiterate the question, because it is more confusing. Absolutely, a number they're calling k, we can call it whatever we want, is put into this function. The output is the same number. Is basically what it's saying. So if they use the same letter ever in maths, then they're talking about the same number coming out. Right, so a good one to think of is, you might think, oh, is it 0? Is it 1? What could it be? If you tried 0 and you added 14, that's 14, you times it by 5, the answer isn't 0. But I like the way we're thinking, because sometimes that is, when it's multiplication is involved, that would often work. So brilliant suggestion, but actually we've got to solve this algebraically. So we're calling the thing k that we don't know. What does the function do? It adds 14 and times it by 5. And that's somehow got a result in the same number k. So as an equation, I'm going to set it up. That would be 5 times k plus 14 needs to equal k. I've put k in, added 14 times it by 5, and the answer should also be k. So now this is just a linear equation to solve. So if I expand the brackets, I'd get 5k plus 70 equals k. And if I now rearrange that, minus the 70 over, minus the k over, so I'd have 5k equals k minus 70. And then if I minus the k, 4k equals minus 70. So this is just solving a sort of linear equation. So k would equal minus 70 over 4. And we could simplify that fraction a bit, minus 35 over 2. And that's sort of its simplest form. You could give it as a decimal, but actually a fraction is absolutely fine. So that's the number that if you subbed it in, you added 14 and you times it by 5, it would actually still come out as that number, which isn't something you could just guess. You would have to go through this process algebraically. So very well done if you followed that. Hopefully that was clear. But yeah, do let me know if there's anything you want to check. So that was a good exam question to have a little look at. Let's keep going and have a little explore of composite functions. And I'd be interested to hear if this is something that people have done before. So composite functions, here we go. Right, and I'm going to just define this now. So the composite function, f of g of x, of two separate functions, f of x and g of x, is basically the function f applied to the function, to the output of the function g of x. So just breaking this down and explaining this simply, I'd be really interested to hear if you've done this before, because I think this takes the notation a bit further and it just takes the idea a bit further of functions. So a composite function is basically a function in a function. So you've got two functions going on. You do one, you put x into one, you put a number into one of them, and then whatever that spits out, you put it into another function. That's what a composite function is. Who has seen this before? You may have seen this notation in past papers, even if you haven't covered it explicitly. Let me know. Who has seen this idea of composite functions before? Right, okay, cool. So we're going to go through it carefully together, but please do stop me or ask anything if you need anything clarified. So there's two functions going on. Lovely, excellent. So brilliant. For some people, this is revision. For others, this is quite new. But if you've got a function f of x, that's a doubling function. That's a function that takes an input and times it by 2. Yeah, I'm sure it's probably been in a lot of mock papers or papers you guys are doing for practice. Now, g of x takes an input and adds 3 to it. No worries. So they're two different functions that do different things. One of them is called f, one of them is called g. Now, if I were to try and find f of g of x, we sort of work from the inside out. So the first thing that happens to the input x is it goes into the g function. So we work, as I said, from the inside out. What happens when x goes into this function g? It adds 3. So the output of g of x is x plus 3. Now that output has still got to go into the f function. So f of g of x, well, I stick x into the g function and it returns x plus 3. That's the new input that goes into the f function. And what does the f function do to it? It doubles all of that, which you could expand out if you wanted, but ultimately that's your answer. So that composition of functions of putting x into g and adding 3 to it, taking the output and then doubling it would be f of g of x. We first apply g to x and then we work outwards. Then we go, okay, now that thing goes into f. And it's really important to realize that the way around you do it is important. F of g of x is generally not the same as g of f of x. The order, we need to be very careful. So if I do it with numbers, if I put 4 into g I could actually sub it straight into this general answer now. I could say, well, it's just 2 times 4 plus 3. 2 times 7, which is 14. Okay. And we could use that combined definition of the composite function. But even if you'd done it separately, if you said, right, what's g of 4? What happens when I put 4 into g? I add 3 to it, and I get 7. And then I take 7 and I put that into f. And what does f do? It times it by 2. I get 14. Okay. So this sort of, the definition here, this is the combined composite function defined in terms of x. So you can just use that now if you need to do the composite function rather than doing it in 2 separate steps. Does that make sense? Let me know if there's anything you want me to specifically clarify. So I think it's a good one to look at as an example, and do feel free to make a note or ask me any questions. We're going to do plenty more of these to just really consolidate this skill, because composite functions, as I said, is a big part of the GCSE, but also moving forward, it's an important part of functions for maths beyond this point. So this is a composite function. Right, so let me get ready to move on. Excellent. So let's look at a few more that might be a little bit more involved. Here we go. So this one here, the function f of x is x minus 4, so it takes away 4. And the g function trebles it, it times it by 3. So if I want to find f of g of x, again, what function are we going to apply first? What does x go into first? What function does x get subbed into? And then we use that result. So remember, we work from the inside out. So this f of g of x, brilliant. G is the first function that x goes into. So x goes into the g function, and that times it by 3. So the output is 3x. Well done, guys. So then 3x is now going into f as the new input. So 3x goes into that function f, which just subtracts 4 from it. So we get left with 3x minus 4. And that's paying careful attention to the order. So could you guys tell me what f of g of 4 would return specifically? Let me know what we'd get. And it'd be great to see some answers for this coming through. Brilliant. Right, some lovely questions and answers coming through in the chat today. Thank you so much, guys. Right, so 3 times 4 minus 4. I'm just directly subbing 4 into that definition of the composite function there. And that will give me 12 minus 4, which is 8. And again, even if you've done it separately, you put 4 into G, and then you took that answer and you put it into F, you would get 8. Because if we put 4 into G, which times it by 3, that's 12. And then if I put 12 into F, which takes away 4, I get 8. Right, this function here, f of g of 3. Now this time, again, let's think about what function it goes into first. X first goes into the g function, which adds 5 to it. And then the f function is applied to that result. Now f squares it, so this will be x plus 5 squared. Now an important note here is that actually x plus 5 squared means x plus 5 times x plus 5. So don't forget that that's also a sneaky double bracket if you were asked to expand it or anything. But when we're subbing a number in, it's actually quite straightforward. We just sub 3 into that and then square it. So let's see what we would get. We'll do brackets first. So we would get 64. Okay. Right, we'll do a couple more because I think this is brilliant practice, and then we'll see again how it might come up in an exam setting. Well done. Yeah, so if you did expand it as a double bracket, you would get a quadratic expression. So very well done if you did that. And it would still return this same answer when you subbed 3 in as x. Brilliant. Right, here we go. So another couple of questions just to get us thinking carefully about what happens here. So you've got the f function, which doubles it and adds 3. And you've got the g function, which square roots it. So again, if I want to think about what would we get if we did f of g of x. Okay, no worries. Let's have a little double check. So we're going to put 3 in, add 5 would be 8, and then square that and get 64. So just double check. And even if you did it separately, it should work. Because if we do 3 plus 5, first of all, 8, then 8 squared, that's what we get. Right, yeah, we need to be careful here that you do BIDMAS or BODMAS. You have to do brackets first. So you have to tidy that bracket up before you square it. So, because otherwise it's a double bracket. Okay, but good. Hopefully we're spotting the little things that will catch lots of students out, and we need to try and be really careful. And if it helps to do them separately as a check-in mechanism, put it into G, then put that into F, then you can kind of guarantee, oh yeah, it still works that way. Brilliant. Right here, let's see what we get. So this is going to be F of the result of G of X. So if I put X into G of X, it gives me root X, and then I need to put that into F. Very well done. Lovely, brilliant questions and answers, guys. So root X now goes in here. So what do I do with the root X? I times it by 2 and I add 3. Okay, and we don't need to worry if it looks a little bit complicated, it's fine, because ultimately we're just sort of subbing numbers in. So if I now were to do that for 25, I do 2 times the root of 25 plus 3. The root of 25 is 5. So 2 times 5. Oh, getting ahead of myself there. 2 times 5 is 10 plus 3. So we're going to get 13 as the output of f of g of x. Right, let's look at this one. And because what happens is when we have composite functions, they do start looking a little bit tricky, but it's still the same process every time. As long as we do the order carefully and correctly, it's the same thing. So let's think about what we'd have here. So f of g of x, if we put g in, what does it spit out? Oops, the pen went a bit funny there. Put g into the x into the function g. That gives me 9 minus 3x. And I now need to apply that, or apply the f function to that. So g of x spits out this. That goes in as the input into the f function. What does the f function do to it? It divides it all by 4. So that will give me 9 minus 3x, the new input, all over 4. Which doesn't look particularly nice, but it is just what happens first. I do 9 minus 3 times that value, take that output, put it all over 4. So then if I now sub minus 1 in as x, let's be really careful here. 9 minus 3 times minus 1, all over 4. And then what we do is we solve that. So be really careful with minus 3 times minus 1. And we're going to get excellent 9. Oh, good, excellent. Some of you are ahead of me here. 9 plus 3 over 4, 12 over 4, which is 3. Very well done. Great. Excellent work, guys. I'm going to keep going. And if you can do another little checkpoint, 1, 2, or a 3, with how confident you feel with composite functions, that would be great. So just a little check, if straightforward, okay, hopefully not super confused, but yeah, if you let me know how you're feeling with that. As I said, some of you, this might be very familiar. Others, it might be new, but hopefully you've kind of picked that up and we're just getting used to the notation. Lovely. Right. Thanks, guys. Hopefully that's good, because if we can feel confident with this topic, it's a really good one to be sort of happy with moving forward into the GCSE exams and beyond. Okay, no worries. Yeah, do you know what? To be honest, guys, that's a really good, honest reflection, is that it is actually the number work and the BIDMAS and the subbing in that people probably mess up because they're paying more attention to the harder bit, that we're more likely to go wrong with a minus sign or a squaring or a double bracket or something, because we're just trying to get the order correct. So let's keep going and see how we go with these exam questions. But really well done to everyone today. And thank you so much for the answers and the questions as we've gone forward. Right, so here is a function, and here is another function, and here is a composite function. So find an expression for m in terms of p, give your answer in its simplest form. So what I think I'm going to do is I'm going to maybe call this function g, call this function f, and actually write what the function is. So g of x, let's think what it does. It adds 3, and then it doubles it. Okay? And then this function here, function b, so I'm going to call this, I'm actually going to call it f, just to stick with that notation. It divides it by 5, and it adds 4. So f of g of x, because I'm going to do function a first, is going to be f of 2x plus 3. So I'm putting that into f. And then what does f do to all of that? It divides it by 5 and then adds 4. Okay. So let's try and tidy this up a little bit. 2, and that'll be 2x plus 6 over 5 plus 4. Okay, so that is the composite function. Now, it's saying that if we put m in as x, the answer is 2p plus 4. So before I rush ahead here, just to check, is everyone happy? This is the first function, this is the second function. The first thing we've done is the 2x plus 3, then sub that into the divide it by 5 and add 4. And then what we can do is we could expand the top bracket and have this. Now, what this is telling me is if we put the letter m in, we're going to get 2m plus 6 over 5 plus 4, and that spits out 2p plus 4. So there's lots going on here, but ultimately what we just need to do is now rearrange and make m the subject. So what we can do is take away 4 from both sides, and then we can times both sides. What we're trying to do, m in terms of p, yeah. So what we can do here is we know that 2m plus 6 over 5 equals 2p. And if I divide both sides by 2, then what we would have is p equals m plus 3 over 5. I'm rearranging that, times up by 5 and minus the 3 across would be 5p minus 3. Okay, you could have rearranged it a different way. You could have times up by 5 and then moved things across and then divided. You would have still ended up with this. But this one was quite involved. Feel free to screenshot or go back over if you want to double check anything here. And do, of course, ask me any questions in the chat. I think this is a really good one to look through because you had to form 2 separate functions in terms of x, sub in the letter m, set up this equation, and then rearrange. But all the steps are processes we've done. So it was a perhaps nastier looking one, but really worth kind of going through. So this is the function we get. This is the composite function. And what we've had to do is put m in as the input and set it all equal to this, and then rearrange and make m the subject. Okay, so I'm going to move this on, but I'm happy to backtrack or answer any questions as the questions get more involved. So one more final exam style question, very much bringing together all the things we've done today. So you've got the 2 functions given. This is a bit nicer that they're given sort of clearly. And it asks us to work out f of g of x. So let's have a little go. F of g of x. So first of all, again, x is going into the g function, and that returns 6x squared plus 3. And that still has to go into the f function. Brilliant. So if I put 6x squared plus 3 all into the f function, what does the f function do to it? It divides it by 3 and then adds 4. So I'm going to write what's happened there. 6x squared plus 3 has gone in as the input. It's got divided by 3, and then we add 4, because that's what the f function does to it. And I can tidy that up a bit because that's divisible by 3. So that would give me 2x squared plus 1 plus 14. Okay, let's keep going. What does that tidy up to? So that would tidy up to, oh, sorry, plus 1, not plus 14. What am I doing? Plus 4. Sorry, guys. Well done. Yeah, good. So that will, brilliant answers. 2x squared plus 5 is ultimately what it tidies up to. And it is in this form. And sometimes this kind of question makes people kind of confused or throws us off or makes us not confident, because it says give your answer in the form ax squared plus b, where a and b are integers. Now, integers just means whole numbers. And my answer is in that form. So we don't need to get too caught up in what it's saying until right at the end to check we have actually done it. Because I think that last line does throw people off. They're thinking, don't know what that means. Have I done it? Is that right? But actually, if you just go through and do what you would have done anyway, that is how your answer comes out. So brilliant. That was really good. So guys, let's have a little recap. So what we've done today is we've written functions using the f of x notation, which for some people is a recap you've seen lots of different times. Then we've gone on and derived inverse functions and looked at the notation of that as well. And then we've looked at composite functions, which is when you have a function in a function. And remember, we work from the inside out. So the input goes into the first function that it's nearest to in the bracket. The thing that spits out then goes in as the new input to the sort of overarching function. And you could have composite functions with loads of different functions involved. But yeah, I think the main idea there was really very much covered in doing that in order, working from the inside out. So if you have any questions, let me know. Thank you so much to everyone for asking questions and sharing answers as we've gone through this. As I mentioned, this is very much a GCSE maths higher tier topic that will carry on beyond GCSE. So getting used to the notation and the style of question is really important. And it's been great to see you guys doing that quite confidently and sharing answers and excellent questions as we've gone through. It is just a little bit of practice and teasing out those things with minus signs and brackets and stuff. Excellent. So very well done, guys. And thank you very much to everyone there. Brilliant answers. Hopefully, I'm going to just stop sharing that there. Hopefully we'll see you at a session soon on the Sundays. And do keep an eye out for upcoming sessions from Snap Revise as you're approaching your GCSEs. It's really good in light of the information coming through from the exam boards and the government of what topics you can sort of be focusing on for each paper. But this is very much an important topic on functions. So really well done to everyone today. Have a great rest of your weekend. Keep well. And again, thank you very much for all the helpful comments, answers, and questions in the chat. It's been lovely to see. So well done, guys. Enjoy the rest of your weekend and take care. That's brilliant. Lovely. Well done, guys. Thanks. Great work.